Hey there, chemistry team! Your chemistry coach is coming at you on another fine, not so sunny Southern California day. Been raining all night long, man. This is crazy. Coming at you with the next video for our complex ion and coordination compounds chapter. This will be video. Let me check it. Number 7. Number 7. I can hold up 7 fingers, right? And we're going to be looking now. So on the last one, uh, we covered crystal field splitting, right? And how octahedral, tetrahedral, square planar complexes split differently because of the geometry as the ligands come in and cause that electrostatic repulsion, thus crystal field theory, which is kind of a subpart of ligand, the whole ligand field theory. What we're going to do now is ultimately we're after how does that affect the magnetism of a complex ion or coordination compound and the color of a complex ion or a coordination compound that it's a part of. So we'll look at colors of complex ions dissolved in solution, or maybe as a coordination compound as a solid. You see, it's just amazing. And all you have to do, you can take the exact same metal ion and just change the ligand, and the color changes of the solution. It's really neat how that works. So we'll look at the 3 factors that really impact magnetism and color, and we'll take a look at those in turn. So, whoop, looks like I didn't erase my board. So my board gets attacked by my kids every night. Little things on there. So let me erase my board and put up kind of an overview of the 3 things we're going to be looking at. And I'll do a little review from first semester general chemistry on electron configuration. So pull out your notes on electron configurations and ion formation. That's going to be important to be able to do real quick. Be right back. Let me clean up my kids' stuff here. Okay, so the 3 main factors that we're going to focus on that have the most impact on the magnetism and color of these babies is 1, the geometry, right? Which we looked at in the last video. Is it an octahedral complex? Is it square planar? Is it tetrahedral? Those are the 3 main things we're looking at because that causes different crystal field splitting, right? Not only the arrangement of the d orbitals, also the energy difference, that delta value, right? We're going to look at how many d electrons that particular metal or metal ion has, because ultimately we're going to put those electrons in those d orbitals. So the crystal field splitting tells us the order that those split and how they fill in, like you're doing electron configuration. Thus, review your electron configurations from first semester general chemistry, right? But we need to know how many we have, because that will then determine the magnetism. Do we have any electrons that are unpaired? Do we have any are all the electrons paired up? So you might want to review paramagnetism and diamagnetism back from last semester as well. For my class, that was chapter 9 material. And then last but not least, the specific ligand, right? Do we have a cyanide ion? Do we have a water molecule? Is it ammonia? Is it thiocyanato, right? That they have different, some are neutral, some are anions, etc., etc. So they're going to have, some will have more repulsion with those d orbital electrons, some will have less. So if there's more repulsion, that's going to create a higher energy gap. We call those strong field ligands, and if it's less repulsion, it's less of an energy gap. The delta is different. We call those weak field ligands. So we've already covered number 1. Boom. So have your notes on the way those d orbitals split. Let's review d orbital electrons real quick and electron configurations. We'll take care of that. And then we'll get into what's called the Spectrochemical Series to determine different ligands and the amount of repulsion energy they have. Are they strong field or weak field ligands? So let me erase the board. We'll do a little bit of electron configuration review. All right, you ready for some review? Blow that dust out of your brain. Figure out what's in there. It's in there. We just got to access it. Electron configuration review. So let's just start with a problem. I'm not going to re-lecture what we talked about last semester. Let's say we have this complex ion, right? We got the cobalt with 4 chlorines or chlorides with a -2 charge. So what is that? Tetrachlorocobaltate. Oh, and I'm not going to say what the oxidation number is, because we're going to have to figure that out to figure out how many d orbital electrons, because we need to know the charge or oxidation number on that ion, because if it's a +3, that means it lost 3 electrons. If it's a +1, it means it lost 1 electron. We got to figure out where those electrons were removed, what orbitals they were removed from, so we can figure out how many d orbital electrons are left over. All right, so how many d orbital electrons does that cobalt have in that particular complex ion? So we need to look on our periodic table and look at how many d orbital electrons cobalt has, right? So let's take a look at our trusty dusty periodic table. And if you look over, cobalt is right here. Cobalt's right here. So that's 1, 2, 3, 4, 5, 6, 7. So that's 7 along in the 3D range. So let's do the electron configuration just for neutral cobalt, and then we'll do it for the ion. So we're going to have like a 4s2 3d 7. 1, 2, 3, 4, 5, 6, 7. All right. So let's draw that just for neutral cobalt. And we'll do the noble gas electron configuration. So let's find the noble gas prior to cobalt, which would be argon, I believe. Right? Argon there, and then it comes down in the next row. So let's put argon in brackets. And I'm going to do the orbital box diagram, right? So the next one is the 4s, and then the 3d. If you remember, there's 5 orbitals, right? We looked through that in the last video. Let's put our electrons in there. So these are filled, 1 up, 1 down, and we have 7 of those electrons in the 3D orbital. So follow Hund's rule. 1, 2, 3, 4, 5, 6, 7. All right, so that would be what cobalt is neutral. We need to figure out what the charge is, or oxidation number is, of cobalt in here. Let's take a look at it. So in this species, can you see that the chloro or the chlorides are a -1 each? I'm not going to write down the algebra. Do it if you need to, right? So I've got 4 of these -1 chloro or chloride ligands. And the total charge must be a -2. So what -4 equals -2? So hopefully you can see from that the cobalt is a +2. So oxidation number is a +2 in that scenario. Which means we're going to look at this neutral atom and go, ooh, we're going to lose 2 of these electrons. Now remember, the ones further from the nucleus are picked off first. So the 4s is going to go, and n equals 4 is a higher n level than n equals 3. So we're going to lose these first. If it was a cobalt +3, we'd lose these and 1 of the d electrons. But since it's a +2, we're losing only the 4s. So let's look at cobalt +2. That will still have the basic configuration. So let's draw this. We got the 4s sublevel, the 3d sublevel. We lose these, but we keep these 7 electrons in the d sublevel. Right? And these were lost. Boom, that's how we got the +2. Now, if you want to do that as just a regular SPDF electron configuration, you could just put argon 3d 7. So we have 7 d electrons. Now, a lot of you will be able to do that in your head. That is perfectly fine. You don't have to waste your time on an exam doing the neutral metal and then figuring out where it goes. If you can just see that in your head and count the number of d electrons that are there. But remember, you always lose the higher energy level s electrons first before you can peel out the d electrons. And just look at the charge from the species, the oxidation number, and that'll tell you how many we do. So again, if that was a +4, I'd lose these and then 2 more. Right? You can predict that pretty easily. So review that for me. We're going to use this technique when we figure out magnetism and color in a later video. Awesome. So let's look at, so we covered the geometry. We've covered how to count number of d orbital electrons. The last one is the type of ligand. Let's look at the spectrochemical series. Be right back. All right, so for ligand type, and this is not a complete list, this is called the Spectrochemical Series. So you just kind of have this with you when you're doing magnetism and colors. The type of ligand, right, depending on its polarity, charge, all that kind of stuff, can have more or less repulsion with those d orbital electrons. So on the far left, have more repulsion, right? The cyanide or cyanato, the nitrate ion, the ethylene diamine, some new ones you haven't seen before. Ammonia, EDTA is a hexadentate one we haven't looked at yet. The thiocyanato connected at nitrogen versus connected at sulfur, the water, the nitrito, the oxalate, hydroxo, fluorochlorobromo. The ones on the far left up here have the most repulsion as you go across. Now these are fairly equally to each other, and they go across. So down here, a lot of those halides as ligands are very minimal repulsion, right? So the greater the repulsion, the larger the crystal field splitting, right? Which is that delta value. So the larger the crystal field splitting, because that more repulsion between the ligand electrostatic, and presence and the d orbital electrons, we call those strong field. Boom, right? If you have less repulsion, instead of a big splitting, crystal field splitting, you have a smaller crystal field splitting, right? So smaller delta values, whether that's octahedral, tetrahedral, doesn't matter. We call those weak field ligands. So weak field ligands, small splitting, strong field ligands, boom. And if you go from the iodo all the way to the cyano, so here's the iodo, you're going bigger, 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 bigger deltas, bigger deltas, bigger deltas, bigger, bigger, blah, blah, right? I love the sound effects, right? There's no distinct line between weak and strong, so I drew a little squiggle there just for our class. So anything to the right of the squiggle, so water over, we're going to consider those weak field ligands. And anything to the left, thiocyanato connected to the nitrogen to the cyano, those are strong, right? But the ones in the middle here, it's a give and take. You can have experimental parameters, pressure, temperature, effects that can actually switch it from a strong to a weak field. So we tend to, in the examples we do, we tend to give more towards the farther side, for sure strong or for sure weak, to make it obvious in the problem. I want a weak field ligand or a strong field ligand. So let's do one more board and talk about why that's important. A small crystal field splitting versus a strong crystal field splitting, and how that's going to affect magnetism and colors in the next couple of videos. So I'll do one more for this, one more board to talk about how does that crystal field splitting compare to putting electrons into orbitals, right? So if I've got a bunch of orbitals and there's an electron in an orbital, I got to put another electron in there. That's called electron pairing energy. They're not very, very excited about that. So the question is, do we pair electrons up, right? Does an electron go into a higher energy empty orbital, or does it pair up into a lower energy already occupied orbital, even though there's an electron in there that it's not happy about? So let's take a look at that real quick. All right, last board for this, and then we have all the arrows in our quiver to be able to answer two simple questions. What's the magnetism of this complex ion? Is it paramagnetic or diamagnetic? And then two, what color would it be in solution or something? Or if it was a coordination compound, what color would that most likely be? Oh, all right. So let's take a look here. Two parameters we're looking at. What's the crystal field splitting energy, right? Based on, is it octahedral, tetrahedral, square planar, and whether the ligands are strong field versus weak field. And then capital P is the electron pairing energy. We're going to look at that in a second. That's the energy it takes for two electrons to pair up in an orbital. All right, so we can kind of put electron pairing energy. In an orbital. All right. Let's take a look here. This would be an example of a weak field ligand, right? So things like the halides, water, those kinds of things, they do a small crystal field splitting. And this would be for an octahedral complex where the dz squared, dx squared minus y squared go up, higher repulsion. The dxy, dxz, dyz split like this. So the same orbital splitting, but if I have a weak field ligand like a fluoro, it won't be very big. So this would be the field splitting, right? The delta value between the two. And then if we had another octahedral complex, but we had a strong field ligand like the cyanide ion or something like that, we get the same splitting of the orbitals, but the crystal field splitting value is bigger in a strong field ligand than a weak field ligand. That's going to be a huge thing. That's going to change how the electrons go into these orbitals. So let's say we had 5 electrons. Okay? So let's say I'm going to put 5d electrons, and we do whatever we have. Let's say we have 5d electrons. If we have the weak field ligand, now this is higher energy, so the first 3 electrons will always go in the lower energy, right? Because they don't pair up. That's Hund's rule, right? Same thing's true over for the strong field ligand. The first 3 electrons would go here. So let's say we have 5d electrons here and 5d electrons here. Same scenario, just strong field ligand versus weak field. That's a cyanide versus a chloride or something. So the same thing, right? We're not going to jump that. The electron would always go into the lowest energy, the Aufbau process, right? So it's going to go here first before it goes up there. So the next one will go here because there's no pairing energy, right? These are degenerate. So it's going to go here rather than there or there. That one's going to go here rather than one of these are up. So pretty obvious for the first 3. The 4th electron, though, boom, this is where it matters. You ready? Imagine you're that 4th electron. You really, really, really want to be in that bus seat all by yourself. You don't want to sit next to a stranger, right? You don't really want to go there, do you? Okay? You'd rather be in an empty orbital. The problem is that's at a higher energy. So you've got a quandary here. It's going to cost you energy to go here. That's the electron pairing energy. If you want to go here, that's going to cost you energy. That's the crystal field splitting. So whether you go as the 4th electron here and pair up, or here to the higher empty orbital, is you're comparing the crystal field splitting to the electron pairing energy. Oh, now notice here for the weak field ligand, the crystal field splitting's low. And the electron pairing energy and the crystal field splitting are pretty close to each other. This is nothing like an n equals 1 to an n equals 2. That's huge. Crystal field splitting's tiny compared to n equals 1 to n equals 2 to n equals 3 energy levels. So these are similar. These are similar in value. So in this scenario, if I compare the pairing energy, the electron pairing energy to the crystal field splitting, right? They're already pretty close to start with, but if I have a weak field ligand, the pairing energy is going to be greater than the crystal. See how small the crystal field splitting is because those weak field ligands? So if I'm that 4th electron, I'm going to go, you know what? It takes less energy to go here up to the next higher energy level because it's such a small gap. Thank you, weak field ligand. Then pairing up. So the next electron will go there when you have a weak field ligand. And then the 5th electron, rather than pairing up, will go there. You see the scenario? Now, if I go over to the strong field ligand and place the next electrons, it looks over here, and you're the 4th electron, and you go, what's a really big ladder to climb? That's going to take a whole lot. I'm going to need to take a lunch break up there and have some Twinkies and some carbonated beverages with lots of sugar and caffeine. It probably is going to be easier to pair up. So in this scenario, the pairing energy is less than the crystal field splitting. So when you have a strong field ligand, it takes less energy to pair up than to climb up to the next level. So the 4th electron will pair up and go, not excited about that, but still less energy than going all the way up there. And then the next electron goes there. So in a weak field octahedral, so you got an octahedral complex with weak field ligands with 5d electrons, they're going to separate all the way through. If you've got an octahedral complex with 5d electrons with a strong field ligand, they're going to pair up. Do you see the difference? Right? This one has 5 unpaired electrons. This one only has 1. So we call this a high spin. High spin. I got a kitty that wants out. And this would be a low spin. All right, so the connection you want to make is weak field ligands create high spin complexes because it's easy to jump up and go into unpaired electron orbitals. A strong field ligand creates a low spin complex because it forces them to pair up in the lower d orbital energies. Pretty crazy. So I'm going to stop this video, study this video, and if you can understand that, magnetism and colors are going to be a cakewalk for you. All right.